Okay, so we have the function f of x this time called 8 over x squared minus 4, and we're looking for the domain, so we're going to grab the denominator and find out what makes it equal to 0. So that involves doing some factoring and solving with the zero product property. So when we get everything done, this is what it's going to look like. So solving with the zero product property and factoring gives us 2 and negative 2. So the domain is basically all the real numbers except for 2 and negative 2. So keep in mind that 2 and negative 2 are basically bad values. They will pretty much be like a critical number for the rest of the problem, and they cannot be labeled as max or min. Okay, so next we are gonna look for the X and Y intercepts. So I'm gonna give you a second here to pause the video and try to find X and Y intercepts. Then I'll provide you with the answers for both of those. So for the x-intercepts, we are going to let y equal to 0, which means we want the fraction 8 over x squared minus 4 to be equal to 0. But if we cross multiply, that means 8 has to be equal to 0, which is virtually impossible. So there is no x-intercept. So this graph does not cross the x-axis. For the y-intercept, we're going to let x be equal to 0. So let's go ahead and plug in 0 into the function and see that we get 8 over negative 4, which is negative 2. So the graph of the function crosses the y-axis at 0, comma, negative 2. So far we have one y-intercept and no x-intercepts, and we have the domain that is all real numbers except for 2 and negative 2, and that's what we're saying up here with the load brace notation. So this means take all the numbers x that you like as long as the x that you choose is not 2 or negative 2. So that's the notation for the domain. So let's go ahead and take a look at the next problem, which is the asymptotes. Again, remember that the function is 8 over x squared minus 4, so for the VAs, we're going to look at the domain, and in the domain we said 2 and negative 2 were bad numbers, basically, like forbidden numbers, so 2 and negative 2 are good candidates here, and they will actually both turn out to be VAs. That's because 2, when you plug it into the numerator, you get 8. When you plug negative 2 into the numerator, you also get 8, so they both make the numerator not 0, but the denominator 0, so they will both count as VA. So we're going to have two vertical lines that this graph cannot cross. Now, what about the horizontal asymptotes? To find the horizontal asymptotes, we take the limit as x approaches infinity or negative infinity on the function f of x. And in this case, this would be the limit as x approaches infinity on 8 divided by x squared minus 4. Now, the degree on the denominator is 2, and on the numerator, there's not even an x. So automatically, this answer will be 0. Okay, so this is basically something that we should kind of remember. If the degree on the numerator is smaller than the degree on the denominator, and you're taking the limit as x approaches infinity, or negative infinity for that matter, the answer is going to be always 0 when this happens. Okay, so let's do the negative infinity version, and so again we get 0. So this tells me basically that at this point y equal to 0 is a horizontal asymptote. Okay, so 0 because I'm getting 0 from here and 0 from there, so automatically that 0 is going to be called horizontal asymptote. And now for the slant asymptote or oblique asymptote, there is none. It's not possible. Again, remember, if there's a horizontal asymptote, there's not going to be an oblique one or a slant one, and vice versa. If there's a slant one, there's not going to be an oblique asymptote. Okay, let's turn our attention to find the increasing, decreasing intervals and the maxes and mins. So in order to do that, we need to have the first derivative, and thankfully, again, they give me the first derivative. Otherwise, I'd have to find it using like a product rule or quotient rule or one of those rules that we learned previously. So again, what makes the derivative equal to 0? Let's go ahead and start with that. What makes the derivative equal to 0 is the fact that the numerator has to be 0. So this happens when x is equal to 0 itself. So that's the first critical number. And what makes the derivative undefined? So let's go ahead and write that down. Those numbers will be plus or minus 2 again, just like we did in part A or part 1 of the problem, step 1, where we found the domain. Okay, so now let's go ahead and do the test and see if the derivative is going to be negative or positive. Okay, so this is what the derivative test is going to look like. The numbers 2 and negative 2 were bad numbers from part 1 or step 1, so these are bad values. That's why I'm putting little circles, not little ticks. So that reminds me not to put a max or min there. And when you do your testing, I believe this is going to be the process. It's going to be positive first, then positive again, then negative, and then negative again, which means the function is going to be increasing, then increasing some more, then decreasing, and then decreasing some more. So when you increase then decrease, that puts a maximum in the middle. So this guy is a maximum. Okay, so keep in mind that 2 and negative 2 are neither max or nor mins. Okay, for two reasons. First of all, we didn't change the sign, so that's why there's not going to be a max or min. The other reason is Well, they were forbidden numbers. Now to find the inflection points and concavity, let's take a look at the second derivative, which again was provided to us. So here it is. And again, we need to know what makes it equal to 0, what makes it undefined. So let's go ahead and start by writing that. Okay, so the second derivative is going to be undefined when the denominator is equal to 0. This means when x squared minus 4 cubed is going to be equal to 0. So that means when x is either plus or minus 2. And remember, these were originally bad numbers from step 1. Now, what makes the derivative equal to 0? So it's going to be 0 when the numerator, 16 times 3x squared plus 4, is equal to 0. The 16 is not going to matter because 16 is always 16. So this means that the 3x squared has to be equal to negative 4. So that the whole thing here will be 0. 0 times 16 will be 0. So one of them has to be negative, one of them has to be positive. And this cannot happen because this would imply that x squared has to now equal to negative 4 over 3. How could something positive or squared be negative? This is no solution. So we only get one answer, which is the plus or minus 2. So let's go ahead and do the test now. Draw the line, and let's find out whether the second derivative is going to be positive or negative and what the inflection points are. Okay, so on the second derivative, we will end up with a plus first, then a minus, then a plus again. So this implies that the function is going to be concave up on the first interval, then concave down on the middle interval, then finally concave up on the third interval. And you know, normally if the function flips like from positive to negative and it flips the concavity, we would have inflection points. But again, the 2 and negative 2 were bad, so these are not going to be inflection points. So no inflection point because the points 2 and negative 2 were not even allowed in my domain. They were bad numbers from the very first step in the problem. Okay, so unfortunately there are no inflection points, but there is concavity happening. So let's put everything together on this graph, and let's start with the X and Y intercepts and the horizontal and vertical asymptotes. So there you get it. The only intercept is on the y-axis, and there are a couple of vertical asymptotes, 2 and negative 2. They were the bad numbers basically from the very start of the problem. And there's the horizontal asymptote, which is y equal to 0 from step number, I believe step number 3, where we find the asymptotes. So at this point, we're going to try to graph the function. And remember, the graph was increasing at first, and we always start next to intercepts, next to asymptotes. So we're going to be increasing kind of like that. And at the same time, it has to be increasing in a concave up way. So we're going to graph the function going kind of sort of like this. And between negative 2 and positive 2, the function was increasing at first, then decreasing. And remember, it has to hit this point right here. So it's going to increase first, and then it decreases after. And it has to be always concave down on that interval. So that's why I'm doing it the way I'm doing it. And finally, on the last interval, the function was decreasing always from the first derivative test, and at the same time it was concave up. So the only way to do that is to have it looking like this. Now again, we're not sure if it's gonna be kind of like that graph that I just made, or kind of like more tight. Is it gonna go down this way? And to get that, we just test with a bunch of points. So like for example, we can put the 3 into the function and see what happens. So if I put a 3, for example, into function, my y-coordinate is gonna be equal to, roughly speaking, 1.6. So 3 will give me 1.6, so kind of like here. So that could give me some guidance that could tell me that the function is kind of like doing that. It's not super tight, basically. Again, I'm not looking for super accuracy, so as long as it has the right shape, then I'll give you the full credit.